In the last few presentations, we had discussion on the series circuits and parallel circuits, and we also derived the formula for the series circuits and for the parallel circuits. And we also discussed a set of rules which are used to find out the solution for any problem which is related to a series circuit and parallel circuits. But from now we are going to discuss networks which are not in a series manner and in parallel manner. So the set of rules which we use for the series circuits and for the parallel circuits are used here to find out the equivalent resistance of this network. Now in this problem we are asked to find out the equivalent resistance between point A and B. So we have already discussed that what is the equivalent resistance, and an equivalent resistance between any 2 points is basically a single resistor which shows the resistance of the whole network between these 2 points. So in this question we are asked to find out the equivalent resistance between point A and point B. Now for that, let's analyze this network briefly. So for that, let's say the potential at this point is, let's say, VA, and the potential at this point is, let's say, VB. So the potential at this point will be different as the potential at this point because there is a resistor connected between these 2 points. Now at the lower portion of this network, the potential at this point will be equals to the potential at this point, which is equals to the potential at this point, because there is nothing connected between these 3 points. So there is no potential difference between these 3 points. So the potential at this point will be equals to the potential at this point, and which is equals to the potential at this point. So let's say the potential at this whole point is VC. So now if you analyze this network briefly, then you will see that these 2 resistors, this 5 ohm resistor and this 15 ohm resistor, are in series because there is only one path available for the current to flow through these 2 resistors. So these 2 resistors are in series. So if the equivalent resistance of these 2 resistors is R equivalent dash is equals to 5 plus 15, which will be equals to 20 ohms. Now for the simplification purposes, if we connect the lower end of this 10 ohm resistor to this point, because the potential at this point is the same as the potential at this point, so we can connect the lower end of this 10 ohm resistor to this point. So the simplified version of this whole network is given as. So for the understanding purposes, we can connect the lower end of this 10 ohm resistor to this point. So now if you analyze this network, so you would see that these 3 resistors are in parallel because the one end of these 3 resistors is connected to this point and the other end of these 3 resistors is connected to this point. So the equivalent of these 3 resistors will be 1 divided by R equivalent double dash, let's say, will be equals to 1 divided by 10 plus 1 divided by 10 plus 1 divided by 20, because these 3 resistors are in parallel. So by using a calculator, you will get R equivalent double dash will be equals to 4 ohms. So we can replace these 3 resistors by an equivalent resistance of 4 ohms by 4 ohm resistors. So now you can see that these 2 resistors are in series because there is only one path for the current to flow through these 2 resistors. So the equivalent of these 2 resistors is, let's say, R equivalent triple dash is equals to 10 plus 4, which is equals to 14 ohms. So we can replace these 2 resistors by a single resistor by the equivalent resistance of 14 ohms. Now if you analyze again this network, then you will see that these 2 resistors are in parallel because the one end of these 2 resistors is connected to this point and the other end of these 2 resistors is connected to this point. So these 2 resistors are in parallel. So the equivalent resistance between these 2 points is, let's say, 1 divided by R equivalent quadruple is equals to 1 divided by 30 plus 1 divided by 14. So if you use your calculator, then you will get, so R equivalent quadruple dash will be equals to 105 divided by 11 ohms, which is equals to 9.546 ohms. So we can replace the equivalent of these 2 resistors by a single resistance of 9.546 ohms. So if you analyze this network again, then you see that these 2 resistors are in series because there is one path available for the current to flow through these 2 resistors. So the equivalent of these 2 resistors are the equivalent between these 2 points will be equals to, the resistance equivalent between these 2 points will be equals to 20 plus 9.546, which is equals to 29.546 ohms. So the equivalent resistance between these 2 points will be equals to, let's say RAB is the equivalent resistance between these 2 points, which is equals to 29.546 ohms. So this is the equivalent resistance of this whole network between point A and B. So it's all for today's presentation. If you have any doubt, ask in the comment section. In the next video lecture, we will be discussing another problem which is related to the series parallel combination of the networks. So see you in the next one.